Okay, so I'm going to review a couple of the slides that we got into yesterday. So we're going to have flat bands that are created from lattices. So the most they can be are fragile, topological, and they're created from orbitals. Okay, finite number of orbitals and finite number of copies. For the most, they can be fragile topological or at James points. For the moment, for these next 10 or 12 slides, we're just going to worry about bands that are flat and that don't have the junction points with other bands, so there's a gap in all the other bands. But of course, what we're doing is also valid in the case where the bands are not exactly flat, but the interaction is larger than the bandwidth of the band, but smaller than the gap between the bands and the other dispersive bands, and the Fermi level is within the quasi-flat band. Okay, but for the purposes of today's talk, we don't want to deal with kinetic energy, and we're going to consider the band being flat, and we're going to project into these flat bands, and the projection operator is this, where you where this matrix U is the eigenstate of the flat band, and alpha beta are the orbitals of the flat bands. Now, this matrix multiplication just takes place over the energies, over the eigenstates of these flat bands. They can be 1, 2, 3, 4, right? Lead for the generalized lead construction that we can narrow, or they basically can fill up so that you can get any number of flat bands that you want, etc. So this matrix multiplication here is over the energy of these bands. If it was over all energies, it would be a complete consolidation. This would be identical, but this is not identical. This is over the energy of these bands. This projector is very useful and is the reason why the projected Hamiltonian is not classical, as was a question yesterday, a very good question yesterday. I encourage you to ask the same. Well, every question yesterday was excellent. So I encourage you to ask more questions, which undoubtedly will also be excellent. So the Hilbert space is now projected. The bar operators are projected into the flat bands. This will be an overcomputed Hilbert space, but it's useful to understand kind of the orbital physics. It's just projected orbital at that position. We can work in band basis, which would be some gamma operators of these bands, and they will be a complete Hilbert space. And the anti-commutation piece as a projection operator. Okay. Now, the Hamiltonian that we'll be using, as I said yesterday, is going to be a Hubbard model of a special type. You can see that this is actually the SZ, the Z component of the spin, of the projected spin in the bands, as will come out in the next slide, squared. But because this is a positive semi-definite Hamiltonian, it means that if I find an energy zero state of this Hamiltonian, then that will be the ground state. Not unique, but it certainly would be the ground state. And because of this commutation relation, which is not zero, because of the projection, these number of operators are not like they were before the projection. They're getting a restricted table space of the projection, and we're not going to get zero by taking the commutation. This Hamiltonian becomes non-trivial. Now, if you expand the squares, as we said last time, and use what's called uniform parity condition, which is something else that we put in order to get some very simple analytics of these models, then you can relate this Hamiltonian to a negative Hubbard model. Okay? And the reason why we're doing this is we want to look at, for example, Hilbert pairing for these, or superconducting graphics for these Hamiltonians. And this analogy, or not analogy, but identity, it's an identity in the case of uniform parity condition, will allow us, by knowing the ground state of this guy, to know the ground state of just this guy, the negative U Hubbard model, because this is a number operator, a projected number operator. So it's number of number of states in the number of particles in the projected bands. Now, as I said yesterday, this uniform pairing condition tells you that the projector, irrespective of the orbital alpha, the diagonal part of the projector, is the same, no matter which orbital alpha you have, and it's also the number of flat bands over the total number of orbitals in the system. Because if you sum over the number of orbitals, this should give you the number of flat bands. So this is the projector in the number of in the flat bands. If you sum over the number of orbitals, but cancel this, okay, then you're going to get the number of flat bands. So that's very easy. And the thing that we said yesterday is that this uniform pairing condition looks a bit strange, but it's not really strange. For example, if I have a lattice where I have two orbitals, A and B, each of them is spin up and spin down. Okay. This is the simplest, well, one of the simplest things we can do. Okay, this is A and B. If I have C6 symmetry, then immediately I'm going to get the uniform pairing condition by default. So symmetry imposes immediately the uniform pairing condition in several cases. If I have a higher dimensional representation or more orbitals on site, then the situation gets more complicated. But in these very simple cases with one orbital per site, like more than one orbital in unit cell, like the graphene case or other cases, lead lattice, for example, also, then I will get uniform pairing condition for free. It's not something that I impose. That's not true. Okay, so what we'll be looking at are many-body ground states. And in order to find the many-body ground states, the tenets of everything that we do is first find the symmetry of the Hamiltonian, and then see how the symmetry can help you. And it turns out that this Hamiltonian, which is just the spin operator, okay, projected spin operator at position R of orbital alpha squared, right? This is the operator. Okay. It turns out that there's a very simple symmetry, which is kind of a generalization of the eta pairing that Young did. It's not the eta pairing that Young did. It turns out the way you get to this symmetry is, okay, the history lesson, Young was looking at Hubble models, not SCs, and up and down on sites plus significant. We found that there's an eta operator named pi, which commutes with the Hamiltonian up to a value, so it gives, the spectrum generated algebra. It turns out that if you kill the kinetic term in the Hubbard model, okay, we're going to have many more eta operators than now. Now, if you project the Hubbard model to some flat bands, all those many eta operators come down to just having one of them, which is this guy. There still remains a bit symmetry, which you see is not at momentum pi, it's at momentum 0. Okay? And you can kind of see it, you can see that it basically is the operator that creates a Cooper pair in the projected orbital. It's the operator that creates a Cooper pair. So it creates a projected electron will spin down, a projected electron will spin up. Now, because this SZ of the electron is, SZ is n up minus n down, but I'm creating an up and a down at the same time, then this operator commutes with S. And hence it commutes with this Hamiltonian. So we found a local symmetry of this operator, of this Hamiltonian, okay, and some eta pairing symmetry. In other words, the charge 2, you can see here, the charge 2 object is a Cooper pair. Okay, so it has an algebra. This Cooper pair has an algebra, just like in Young's description, even though this was at momentum pi. And moreover, it immediately gives us the ground states. Okay, so what we said is that this operator commutes with the eta operator. Hence, if I take the vacuum, which has energy 0 under this operator, and I take the eta operator and hits the vacuum n times, small n times, this is a state of 2, times n particles, and I can hit it a thermodynamic number of times, then this will also be a zero energy state of this Hamiltonian, and hence it will be a ground state. So there's many zero energy states of these ground states, of these states. Now, of course, these look very much like the PCS wave functions, right? Because this eta operator is just hitting the state n times. So in effect, you can build a number of non-conserving ground states, which is the PCS ground state. You just take this to this eta operator to the power here. This mixes particles 0, 2, 4, etc. This is like the PCS wave function. Or you can work in the particle conserving formalism, where I conserve the number of particles, which I will refer to. And if you do this, then you get that each of these is a ground state at different numbers of particles. And then what you can compute in some boundary basis is the off-diagonal rates that are defined like this. Okay, we find that it's finite, not only that it's non-zero, but it is finite at finite filling, is near the filling of the bands. So this turns out to be a very, very more and more to look like a superconductor. Well, it's got the same wave function. It's got this eta operator that creates Cooper pairs. They're actually Cooper pairs on site. They're given by these projected operators, okay, projected on-site operators. These projected on-site operators, because of this bar, have some spread. Okay, if they were just purely projected on site and had no spread, then this would basically be just local bound pairs. But they have some spread, and we'll see how the spread helps us. Okay, now we want to characterize the superconductor that we have, and we want to find out its excitations. Okay, so there's several ways to do this, and I think we'll get to some just by graphing. And I want you to remember this, because this is the same thing that we're doing just by graphing that Nikolai and Gallup already explained. That basically it's just the Hamiltonian. We're not going to look at negative U-Hubbard model Hamiltonian, the positive U-Hubbard model projected Hamiltonians, but it's really the same type of situation. Okay, so then John Allen and Cook and Ivy, what they did is basically said, okay, well, we have the ground states, this n ground states, which is a particle number 2 times n, which are the eta operator to the power n times the vacuum. Okay. Let's see if I can find the single particles of it. Well, a very easy thing to do is just to hit the ground state at particle number 2 times small n, hit it with a creation operator of the electron in the nth flat band. Right? So we were talking about these operators C, K, alpha, sigma spin, alpha is orbital, projected in the band. These are just sum over the flat bands, okay, of some the eigenstates of the flat bands times gamma of K and sigma. And here, assume no spinor decoupling. You can actually add spinor decoupling as long as you keep some symmetry. Assume no spinor decoupling here, it doesn't matter. Just gives you richer things, but it doesn't matter. So, this is a complete basis. Okay? And there's a unitary transformation from this to this basis. Okay? And okay, so then you try the ansatz of having as a charge excitation on top of this ground state n, this gamma dagger of the flat band comes in. And you ask what is its energy, and you find the following equation that this, because, and this is true, only the n is the ground state of the Hamiltonian cage. Okay, and you find that that this due to uniform pairing condition, which is important, this just gets this is basically this commutator just computes the energy in this excitation minus the energy of the ground state. Okay, so just the gap between the ground state and this excitation. And you find that this is special with these models that the result is contained within the one particle Hilbert space. In other words, it doesn't have things of this type. It doesn't scatter to things of this type. Okay, to a particle plus the trion. Okay, it doesn't scatter to a trion. And this is important for this type of positive semi-definite Hamiltonians. They have this property. Once you found the ground state is basically kind of non-interacting, right? So it's kind of a slave determinant here. It's this 8 operator added many times, but it basically looks like a non-interactive ground state, but just Cooper pairs. Okay. Then we're going to find that you don't scatter trions, and then if you're scattering to trions, you need an equation for the trion, or scattering to whatever it is, quintons, etc. So you find that the scattering is very nice. This scattering is very nice, and then the single particle energy is just diagonalizing a matrix. Okay, so it becomes really diagonalizing the matrix, and you find out that with the uniform pairing condition, the gap is constant. So the charge excitation has a flat gap, and this is a consequence of A having this type of positive semi-definite Hamiltonian. So you get consistency within the one particle, but you don't scatter into trions. And 2, having a uniform pairing condition. And here, this flat pairing gap is this one. Okay, so we have a single particle, this is with PDG quasi-particle, this gap. Now, of course, what you want to do is you want to go and see the charge 2 excitation. And the reason why we want to see the charge 2 excitation is because that's going to give you the Cooper pair. Okay. Now we know the following thing. We know that n, which is eta, is 8 operator space to the vector n times 0, is a ground state. But we also know that n minus 1 or n plus 1 is the charge plus 2 excitation, which is eta dagger to n plus 1. Okay, which is a 2-particle above this, so it's contained in this here. Okay, there's also a ground state. So it means I must have a 0 energy excitation here. Okay, and that's actually the maximal binding energy of the Cooper pair. This is a system where the Cooper pair has a large binding energy. Okay, and what we need to look at is the stability of this Cooper pair spectrum around its 0 energy. Okay, so if you do now the commutator of the ground state of 2 n particles times plus 2 creation operators in the flat bands, this creates another 2 particles in the flat bands. You want to find out its energy. The scattering equation again becomes rather simple because of this positive and these Hamiltonians. It becomes rather simple, and it's just 2 particles. Okay, and because this state is simple, and it's self-contained with a 2-particle space of the state times a matrix here. Okay, and the properties of this matrix are very easy to analyze. Okay, the property of this matrix are the following. First of all, we're going to get what's called a particle-particle continuum. Right? So the particle-particle continuum. Remember, we said that the particle gap is epsilon u over 2. Epsilon was the number of flat bands or the number of orbitals was the uniform pairing condition. Okay? So we said that this is the energy of one PDG quasi-particle. Now, twice times that, of course, since I have 2 quasi-particles, I'm just getting the particle-particle continuum here. But then I also have a scattering matrix. Okay? And this scattering matrix can give you bound states, anti-bound states, or splitting in the generically or splitting in the two-particle continuum. So let's see what it gives. Okay. So the simplest case is the case where this is a triplet. Okay, excitation. So sigma and sigma prime are the same. Say both the number. Okay. It turns out that in this case, since S is symmetric, what you're going to get is the scattering and the fermions are anti-symmetric. What you're going to get is that this, when contracted with the fermions here, you're going to get 0. So the triplet excitations are just two decoupled electrons. Okay, they have charge epsilon times u, which is twice times the charge of one particle excitation. This is starting to look very trivial, so you can wonder if I'm putting a length and told you that yesterday something non-trivial happens. But it turns out that something non-trivial does happen. It can happen exactly. These models kind of take out exactly the fundamental property that you want to associate with a topology. And this is a spin. This is my 8 operator was in the singlet sector. Remember, 8 operator was C up, C down dagger. Okay, the dagger was C up, C down dagger. Projectors, etc. This was in the singlet sector. So we want to look at the singlet excitation, two-particle excitation. And this also has a two-particle continuum. But now they have a matrix S up down. And direct computation of this matrix gives you the following. Okay? This S matrix is negative semi-definite. You can see it here. So this is a matrix, so any matrix n and dagger is positive semi-definite. You take the minus of that, you get negative semi-definite matrix. There's only negative matrix. Okay. So now we've established by Bayer's theorem that this is the largest energy scale in the spectrum. So the particle-particle continuum. Right, for this two-particle continuum, which is flat because the two particles are flat. The particle-particle continuum is the largest energy scale in the problem, and now we have bound states because this is a negative semi-definite matrix. And there's a theorem you can check. So the Bayes theorem basically tells you that we're going to have bound states from here, and the spectrum is bounded by here upwards. Okay, and this U matrix, this I guess map cow U, which changed this confusing with this. This matrix is just a product of the eigenstates. This normal U is the eigenstates of the flat bands. So n and n run over the flat bands. Okay, and this is this matrix. And you see spin up and down the star because we use time reversal with the so anyways, so you get this matrix, and as I said, it's negative semi-definite. Moreover, the fundamental thing that you have to realize here is that this matrix has a large number of zero eigenvalues. So you can ask, I said that this matrix is negative semi-definite. This is a two-particle continuum. Okay? And if this matrix was negative semi-definite but didn't have a huge number of zero eigenvalues, then I could imagine it splitting the two-particle continuum. But it doesn't, because there's a huge number of zero eigenvalues. Okay? And the way you can see this is the following. You can see here that the number of non-zero eigenvalues of U dagger and U is the same as those of the matrix of U dagger is the same as those of the matrix U dagger and U. Okay. Now this matrix U dagger and U here, okay, has dimensions alpha order, not something, but it's an order of alpha beta. Okay, so the number of non-zero eigenvalues of this S is basically bounded roughly by the number of orbitals times some factors. Okay, so in that sense, we expect that it's governed by a small Hamiltonian. Right? Everything else is zero eigenvalue. So So the non-zero eigenvalues of this S matrix, which up to a shift, because this guy is here empty, okay, up to a shift are the eigenvalues of the two-body spectrum up to an identity shift. Are governed by a very small Hamiltonian because this matrix has a lot of non-nodes with non-zero energies are given by a small Hamiltonian, and this is the Hamiltonian. This is just this H, where you replace this math cal u with this u here, and these are the projected operators in the flat bands that we defined before, right? Just the projection operators in the flat bands. The two-body spectrum has a Hamiltonian, which is basically number of orbitals here, the non-zero eigenvalues, and this product of the projection operators in a single particle flat band. Okay, it's a concatenation of this or convolution. It's a single particle. So this is the effective single particle matrix for the two values of separation. And now let's look at the spectrum. Okay, so as we said, the two particle spectrum gives you a continuum of unfair states. There's a huge amount of states here of order number of unit cells, okay, of order. There's some factors for flat bands. Number of unit cells minus number of orbitals. So this is a thermodynamic number of unit cells per number of orbitals per series. So the thermodynamic number of states in the particle continuum. What we're interested in are the bound states. Okay? So you can look at them here. Now, this is the zero energy state, which is just eta dagger to 2n plus 1 times the vacuum. Okay? And you know it's got to have energy zero because that's something about grounded, and it sure does have energy zero. Yeah. But what you're interested in is the mass or the stiffness of this pair. So this is your Cooper pair, which basically tells you that if I make two electrons, one will spin up, one will spin down. Okay, each of them has energy, whatever this is, epsilon u over 2. Okay, so together they have epsilon u, but there's a binding energy between them, which basically now drops their energy down, and this binding energy is maximum. It's the most of them have. So there's a binding energy which drops their energy down to 0. Okay, so then this is the first thing, and as a corollary of all the states, it turns out you can use all the formulas that I told you about to get the representation of these bands, and to get the topology of different modes. So, for example, in this case, it's two particle modes here, which is a bound state, but not exactly 0. Let's try the topology exactly, etc., etc. So you have a formalism that can get you the topology of the bound states. But we're going to concentrate more on this guy. And for this guy, what you can prove, what John Allen tried to prove, is the following thing: that the mass of this is, for example, another model, the mass of this thing here, the mass of the is actually given by the quantum metric in the system. It's given by a minimal quantum metric which you can get to. It's the lowest possible quantum metric in the system. So which you can get to is the one that's protected and bounded by the code actually. And you can see here out of this Hamiltonian for this Cooper pair, you can prove the following thing. And this is the highlight of this vacuum part, that the energy of this is quadratic with a mass tensor exactly given by the quantum metric. So this is how topology or quantum geometry comes into these interacting problems. It binds the okay, the spectrum. For example, this spectrum was flat, okay, so this spectrum didn't have stiffness, okay? So the spectrum looked something like this. Then I would know I'm not in the correct ground state, okay? Because I would know I can lower my energy by condensing these photons to another ground state like finite energy, for example. But we know here this cannot happen, okay? Because of these, okay, so we know this cannot happen, and this is because of the stiffness of the Cooper mode of the collective mode, which comes from the minimal quantum geometry of the system.
Can we ask
Now,
a question?
yes, go ahead.
So I think slide before. So just to make sure we fully understand, the reason why you cannot see the flat band is because the flat band is actually in the non-interacting picture. So the slide before you show us like 3 or 4 bands, right?
So yeah, so the non-interacting flat band.
Okay.
You can kind of, I mean, normally if I project, so let's do the following thing. Let's take a non-interacting flat band and project it, and take a Hubbard Hamiltonian or Hubbard's negative Hubbard and project it. And I don't tell you it's a non-interacting flat band. I just show you the interacting spectrum.
Okay.
Normally, you wouldn't be able to tell me. I mean, there could be some hints that this non-interacting, that this interacting spectrum is coming from a non-interacting flat band. But normally, I don't see, or I haven't really thought fully about it, but I don't see any way that if somebody gives you an a priori spectrum, you're able to tell, this is from a flat, this comes from a flat. Now, here you can tell. The reason is that in this case, uniform pairing condition makes this number of states, the particle-particle continuum, flat. And I'll show the graphing case. In the graphing case, which doesn't have, in the twisted bilayer case, it doesn't have uniform pairing. This spectrum, this continuum of Ampere states breaks up and becomes very large. Okay, the particle-particle continuum. So in this case, you would be able to tell me, you'd have a hint. Like if I saw this spectrum, if I was given this interacting spectrum, the first question I would ask is, why is there a huge thermodynamic number of planets that are exactly flat here? And here you'd sort of be able to guess that they're coming from a flat band. But the interesting thing, so this is we can prove this with the flat band with the uniform pairing condition will have this huge degeneracy. Will have flat one energy. So you'll have this one particle spectrum is flat, for example, charge 1 spectrum. And with a charge 2 spectrum, even if you gave me the charge 2 spectrum, I would be able to tell you, there's a flat band hanging around because I have a thermodynamic number of states here. But so this is because of the uniform pairing condition and the projection of the flat band. But what's interesting about these models is not what they lack, which is a dispersion for the particle-particle continuum. What's interesting about these models is that they basically capture the collective behavior, right? They kind of like immediately give you an analytic way of understanding the collective behavior. So you see, like these modes, for example, here there's 3 modes, right? There's 1, 2, and 3. So they're described by 3 by 3 Hamiltonian. Okay, this is the Hamiltonian. So the collective modes of the charge 2 collective modes of the system are described by 3 by 3 Hamiltonian. So this is very special for this model, but it's also very powerful in the sense that it enables you to prove these bounds for the Cooper pair mass. Okay, have I answered your question, sort of?
Yes. No. We can have one question.
More questions?
Yes, there are more questions from Wagner. Yeah, 3 questions from Wagner. First, I think in the previous slide, there's a question about normally eta pairing is for the pairing between k and pi minus k, but here it seems to be between k and minus k. What is eta pairing here?
That's right. So this is, as I said, it's not exactly the eta pairing of C and Young. Okay? So the eta pairing of C and Young is k pi minus k. Okay, there will be the eta period. Okay, so this is not. But it's still a charge 2 operator, so we're going to call it eta pair. Call it eta symmetry, eta pair. You might think of it as an abusive language. It's a charge 2 operator. It's just not. The only reason why CNN needs this pi operator is because he wants the kinetic energy in the Hubble model, okay, to give you 0. But the kinetic energy in the Hubble model depends on momentum. And if I have this operator, then the eta dagger times the kinetic energy in the Hubble model, the kinetic energy will give you something proportional to this times whatever C dagger C. C dagger C dagger. Okay? So we give you something proportional to this. Now, you remember in the Hubble model, epsilon of k is cosine of k. Okay? The cosine of k plus cosine of pi minus k is 0. And that's why Tianyang, etc. They looked at the pi operator because they wanted to kill the kinetic energy in the computation. We don't have kinetic energy. Okay? So in principle, if I just have a classical Hubble model has a huge number of symmetries, not just the data pair. If I take C dagger K1, C dagger K2, those would be symmetries of the Hubble model. Actually, symmetry spectrum generated algebra of the Hubble model. Okay? But then if I project onto the flat bands, only this one remains. Only this one with a minus k. So out of the huge number, if I project in the flat band, the Hubble-like model, it's the Hubble-like model. It's not an up and down. If I project it with a positive Hubble, it's an up and down with a negative Hubble, that comes out of U S squared. So we call them Hubble-like. Okay? So if I project that to the flat bands, it's no longer commute. Out of that huge set of symmetries that's the living Hamiltonian have, once projected, only this one. Have I answered your question?
Yes, thank you. Wait, we have another question.
Thank you, Professor, for your talk. Sorry, this is more of a clarification question. Is it too long? Oh, wonderful. So I just want to ask, basically the mechanism that drives the Cooper pairing in the system is the on-site electron interaction rate.
That's right.
I see.
So you know that this would have to superconduct, right? Mm-hmm. But now imagine I did this, and these were not projected operators. Okay.
Yes.
So let's say these were not n bar, but they were just n.
Like normal bands, okay? Yes.
With n squared is equal to n. This is the normal operators, mm-hmm. and the normal operators commute. So n r alpha and r beta commutator is equal to 1. Okay, is equal to 1. Is equal to 0. Okay, whereas these guys don't commute. Okay, so if I did this, if these didn't have the n bar, okay, this would be a negative U Hubble model. So what would happen is my phase, what would be the lowest energy? Well, I know what would be the lowest energy. Every site occupied, doubly occupied. You agree? So every site is doubly occupied. So I have the sites, right? Because I lower the energy. So I have a charge 2 per site. But these charges cannot move. Okay? So this is just a paired system with a huge gap, which is U, to charge 1 excitation. Okay? But the moment you try, the charges are confined on site. Right? The pairing is on site, so you just put the 2 charges on site and they stay there. Mm-hmm. So this, for example, in the Cooper spectrum, I didn't have this bar, which brings you everything. It brings you that the mass of the Cooper there.
Yes.
If I didn't have this bar, okay, the charge 2 spectrum would look like this. I would have U energy here times epsilon. I wouldn't have, if I wouldn't have it, I wouldn't have epsilon. I would have U here. Okay. I would have a zero Cooper pair here. Okay. But I wouldn't have any stiffness. In other words, my Cooper pair would have no mass. Okay. So there's no, so the superfluid stiffness would be given by this. You know, like it's like a goldstone stiffness. It's like basically what makes the system stable. It's given by the quantum geometry. So if you don't have any quantum geometry, i.e., no projection, then you don't have any superfluid weight.
So how will we implement the projection in like real systems?
Well, the projection is implemented in real systems by the following properties. If I have dispersive band and sort of flattish band, okay, my number one Fermi level is in this flattish band. Number two, U is larger than the bandwidth of the flattish band, but smaller than this. Then physically, you're in the regime of the projection, smaller than the gap. Okay, because your Fermi level is in your flat band or flattish band. Upper U is larger than the flattish band, so you can think of all the degrees in the flat band as influenced in the same way by upper U, and upper U is for interaction. And interaction is smaller than the gap. So that's the regime of projection. Does that make sense?
Yes, thank you so much, Professor.
Sure. Very good questions. So the regime of projection is not just something made up. Very good. More questions, please.
Okay, maybe I can ask the next one, which I just asked Jonas that is sitting next to me. About so if he found the gap, so can you say something about the critical temperature? So we know that, for example, when you have flat bed and you see superconductivity, like in the experiment, so the scanning of with the critical temperature is actually interesting for electrical and inclusive biography. So in your model, can you say something about the critical temperature?
Right. So this model here has a pseudo gap. So this is 2D models. So this model has a pseudo gap. So the critical temperature is basically the pairing temperature, the pseudo gap temperature, is basically the gap of the PVG, the one particle excitation. So it's a very good question. So this is the pseudo gap. Okay, so KT is equal to this. So you see it's proportional to it. But then actually, since these are 2D systems, they have a Costa-Vestalis transition. So in effect, the pairing, when the superfluid gets coherence, is given by this by the superfluid weight. So there's two temperature scales in this problem. Right? So one of them is the pseudo gap, which is just the binding, which is just the charge one excitation, and the other one is the superfluid weight, since you're this is 2D superconductor. So that's actually governed by this in some way that you can derive. Okay. So and if again, if I just had this flat, it wouldn't see that. It wouldn't get superfluid stiffness. So although you have a pairing gap on site, so spectroscopically you see a pairing gap, but does that answer your question? Okay.
Yeah, actually, well, so you're saying we supposed to have two critical temperatures? Like, because you said there are two important temperatures. So I would see two transitions?
Yeah, I mean, I'm saying that there's the pseudo gap temperature is not, the pseudo gap phase is kind of it's basically this, you'll start seeing it's kind of like this crossover. You start seeing because you lower the temperature and down. This would get broadened by temperature, right? This one particle. So, but this one particle, but this spectroscopically, we try to inject an electron, right? We sort of break a pair here, which is kind of, and you see a gap of order, right? Now that doesn't mean that this thing gets coherence at this temperature. That's given by the superfluid weights through the KT transition. So I wouldn't call the pseudo drop temperature as an order. The system doesn't get stiffness at this temperature. Does that make sense?
Yes, yes. Thank you so much.
Thank you. Very good question. More questions?
Yeah, which one now?
Okay, very good. Okay, so while doing this, Joe and I are in Kuka and Heidi got really excited because it turned out you could build a model, okay, that's got uniform pairing. That's got this uniform pairing that makes the spectrum of collective nodes just come out at you without all the poo-pooing of the single particle contingent. Okay, and you could build such a model, for example, with non-trivial with uniform pairing condition that looks very similar to twisted bilayer graphene. Okay, out of I guess you still would break particle hole. We'll see very soon. You can break particle holes, so you just have to break some symmetry. But you could build a model with in the same way that the generalized lead method that we presented before, that, you know, several lattices and something continuum. That looks very similar to twisted bilayer. Look at the spectrum here that people will notice the bilayer. This looks very good. Okay, and then you could get, for example, nice Cooper pair spectrum, for example, all these states. Okay, okay. Unfortunately, although this was very exciting at the time, it turns out that these bands here have actually twice the topology of the twisted bilayer bands. Okay, now we're going to go to twisted bilayer and show that there's two things that happen in twisted bilayer. Thing number one is that there's another mechanism for flat bands that basically doesn't happen in, you cannot obtain it from, if you want to respect all these things, you cannot obtain it from these type of generalized loop constructions, even though a lot of people tried. And number two, that even though the uniform pairing condition is not satisfied, okay, even in the models where you break some symmetries in the twisted bilayer, you can still use similar methods to obtain the spectrum. And a lot of the things that we've learned so far will be shown in twisted bilayer also. Okay, so let's go to twisted bilayer graphic. So, just as I showed you before, that model had uniform pairing, but it wasn't giving the correct topology of the twisted bilayer bands. There were other attempts to write the twisted bilayer bands as orbital models. So that's finite number of orbitals. The idea behind these attempts is good in the sense that if you have an orbital model, you can just, the less orbitals you have, the better. You can just, you know, do some, you can deploy numerics into DMT or other things that people are doing. Okay. So
can we ask one more question before continuing?
Sure.
Okay.
Hi, Professor Bernevig. Thank you very much for the nice talk. Actually, I was wondering, can we study excitons or trions for the flat bands and the scheme that you have described so far? Yeah, and for example, how excitons are distributed for the flat bands in real space, or their corresponding properties.
Yeah, so that's a very good question. So this scheme allows you to actually to solve for, you know, charge neutral or charge or trions or quintons, etc. So now, for example, I didn't show the charge neutral excitations here, but there's charge neutral excitations that actually have zero gap, but there's charge neutral. There are anti-bound states. Okay, so there's bound states and anti-bound states in the charge neutral excitation. Now, for the trions and the other ones, and this is something that Joe and I are looking at now, so it's actually, you know, after we split up, and we can talk to Joe on the latest updates of this, because I might not even know. We believe that some of these models could actually potentially be integrable. So we can get to the trion spectrum exactly, we can get to the quinton spectrum exactly, etc. And that's just because certainly if you just go to larger number of, larger number of particles in top of these states, you still get a lot of zero modes. There's a thermodynamic number of, not zero modes, but zero modes with the scattering matrix, which means just particle continuum is flat. And then there's, finite number of collective modes. So certainly the method allows you to do it. And once you do it, then of course gets the real space hexagon, which is just a charge zero station. You can get the spectrum, you can get, many things. So that's on our to-do list. That's very good question. And I'll show you, for example, the hexagon spectrum just to find out that. The moral of the story is that they look, it looks the same. We have a spectrum that goes to zero, which is the largest bound state, and then you have some other bound states in the particle holding, etc. Does that answer your question?
Yes, thank you very much.
Thank you.
Okay, thank you.
Okay, thank you. Very good. Okay, so what I have to say, and I'll go fast about these models, is that they break some symmetries. In other words, in the twisted bilayer, for the people that know this model called the distance and model, the distance and model per value cannot be ever written down in terms of a finite number of objects. And you can ask me how can that be? And the answer is that the distance model is a continuum model. It's not a lattice model. Since the continuum model, it might not have a real space. So there's no contradiction in this. But what is interesting about the distance model per value is that it's actually anomalous. So it's kind of similar to the surface of a TI, where you have a single Dirac node that you can never have in a bulk. However, in this case, you have two Dirac nodes, the flattish bands, and it's not a surface of anything. That's an anomalous model. So we'll see how you get that. And because you cannot write it on the lattice, this is a different class of flat band models. Okay, they come out of the continuum. And they're more similar in some limits to lambda level. This heavy fermion picture that I probably won't get to. Well, for sure I won't get to. Shows that they're not very similar to the quantum geometry is not very similar to that of lambda levels. Okay, so let's understand. So the purpose of the next 20 minutes is to understand the spectrum of this matter in light of what we talked about for the uniform Perry condition, and I'll point out where the difference with uniform Perry condition comes. Okay, so twisted bilayer is a system where you take two graphing sheets, you rotate them by an angle. If you rotate them by an angle, then what happens, this angle here is small, but imagine this angle being 1 degree. Then what happens is you get a small Brillouin zone at each value, and the value is formed by the K point of the lower layer and the K point of the upper layer. If this angle is small, in order to get, and this is the K prime point, okay, of the lower layer and the upper layer. Okay, so if this angle is small, in order to get from value K to value K prime to mix them, what you need to do is to do perturbation theory. And perturbation theory in the interlayer hopping over the intralayer hopping will be T perpendicular over T parallel, okay, which is at the order of whatever 0.1, just and the order of this perturbation theory will be the order of tilings of this Brillouin zone, the small Brillouin zone, from value K to value K prime. Now here it's a saturated angle, but you can see that this Brillouin zone, the moire Brillouin zone, the small Brillouin zone shrinks as you get to small angle, and to get from one K point of the original graphing lattice to the other K, to the K prime point of the graphing lattice, which is a huge distance, you need to go 1 over theta times, okay, with a small Brillouin zone. This is a very small number when T vertical over T parallel is less than 1. Okay? And the coupling between values is exponentially suppressed, and that's why you get what's called the value quantum number. So we have a spin quantum number, a value quantum number, and then 2 bands per value per spin. And these two bands are described by this Hamiltonian, which is this Hamiltonian, which is the Dirac node of the upper layer of K. This is for value K. The Dirac node of the lower layer of value K, and some hopping, okay, in between the layers that couples them. And this hopping is at the Morel wavelength. This is the large Morel wavelength. Okay, well, the small Morel wavelength, the large Morel wavelength. Okay, and this hopping has what's called an A coupling. And the A coupling is the AA regions of Morel, where if you look at it, it looks like the A's atoms of the lower layer sit on top of the A atoms of the upper layer, like this. And this is the AB hopping. You can see it's off diagonal here. In sublattice indices. And W1 is the regions of just its bilayer. I'm not sure about the picture here, but you can see some regions where you see AB type hopping. So A atom of one person. Okay, so you have the other layer, and then you have an atom in the middle of the hexagon. Okay, so then this is, there's two parameters, W0 and W1, and this is called the Princeton Hamiltonian. And the Princeton Hamiltonian, there's a remarkable thing about it, is that if you're going to correct all the symmetries in the Princeton Hamiltonian model, what will happen is that, right, the Princeton Hamiltonian model has a Dirac point at the K of the upper layer, which we call K Moiré, a K at the lower layer, which we call K Moiré prime. Right? So K Moiré prime is the K of the upper layer, K Moiré is the K of the lower layer. They both are from value K, and there then the T, okay, the T of R does splittings of degeneracies and eventually creates flat bands or flattish bands. But what's remarkable about it is that symmetries alone constrain the representations of the two flat bands, of the two bands around charge neutrality. I don't know if they're flat or not, right? The flatness depends on whether I'm in a magic angle or not. But if I'm not in a magic angle, they're not flat, the representations remain the same. So in other words, I wouldn't know if gamma 1 is above gamma 2 or gamma 2 is above gamma 1. These are crystallographic representations, and these are the characters under the symmetry scenario. But these things will stay like this. In other words, I cannot have gamma 1, gamma 1, and 1, and 1. Okay? And this is a symmetry argument for any small angle. Okay, so whether you're at 1.5, 2, or 0.9. Okay, this representation is really the same. And the fundamental thing about this is, as I said, every time we have representations of a set of values separated from others, go to the larger server and find if you can write them down in terms of atomic units. And in terms of output, you cannot. Hence, these bands are topological. Yet another set of flat bands that's topological. Now, you can ask what kind of topology they have, okay? And at the beginning, it was thought that this topology would be fragile, but it turns out the topology is actually stable. So this is, you know, a kind of crop of the Princeton Hamiltonian continuum model. It's called a continuum. There are also other people who can claim building such models. Okay, so for the continuum, this is like models. These are the representations of the flat bands, and this is a snapshot within 50 to minus 15 electron volts. And these representations of the flat bands are fixed by symmetries, okay? And they're topological. And it was thought that they're fragile topological, but it actually turns out that if you do a Wilson group of any number of bands, so not just the two bands, so fragile topology would mean that if I take these two bands and add other bands to the system, I can make them trivial. And this is what these 10-band models do. They add other bands to the system to make them trivial. So these bands trivial, then represent them in terms of orbitals, which we talk about. But it turns out that in the process of doing that, they break the symmetry. And the symmetry that they break is the particle Hall symmetry of the system and continuum models. And this particle Hall symmetry is better than neglecting spin-order coupling. Normally, we all neglect spin-order coupling just a bilayer or in any graphing system. Neglecting spin-order coupling gives you the same error, or actually larger error than saying that the system has particle symmetry. If you impose particle symmetry exactly, actually this Wilson particle symmetry is not imposed exactly, but we can't see it because the deviation is so small. You can see that no matter how many bands I take, the Wilson loop spectrum still wants. Okay, so there's no way to localize it. The Wilson loop at the very phase wants, very phase the Barnier center. There's no way to localize it. Take it because if it was localized, it wouldn't change with momentum. But if it winds around, this is pi to minus pi periodic, you can never make it flat, right? Something that winds and goes across a large circle, I can never localize. So it turns out that these distant normals are stable topology and they're actually anomalous. They actually have 4 n plus 2 Dirac points in any number of bands from minus to irrespective of you're going to look at them. You can always find the 4 n plus 2 Dirac points there. It's in a similar way, the surface of a TI is anomalous. You're going to find 1 Dirac, okay, for whatever 4 n plus 1 for in this case, it's 4 n plus 2, and it's not the surface of anything. And it's still anomalous. Okay, and I told you that these bands, I'm going to go for like 5 more minutes. Stop with the question. I told you that these bands are actually, there's 2 values times 2 states times 2 bands. So they can be occupied by 8 electrons. So you can go from a filling of minus 4 to 4, where 0 is charge neutrality. And these are single particle gaps of the system or continuum model type. And you see insulating states of integer filling. Actually, depends on which integer filling. Actually, filling 1, probably some other states, translation, symmetry break, some other state comes in, etc. But at 0 total, let's assume you see insulating states of all integer fillings. So insulating states of -3, which means that your single particle picture broke down, because if I have the single particle, anything from -4 filling -4 to 4 would have to be a metal, not a insulator. So it means that these are not states. Okay, so now we're on with what we've learned so far, and we can do a strong coupling extension of just by the Hamiltonian, which I would say more recently is kind of a heavy Fermion expansion, but I don't have time to talk about this. So this basically projects the Coulomb interaction, which now is repulsed and not attractive, and it's just density Coulomb interaction into these bands. Okay, so it takes this Coulomb interaction, it projects into these bands, and these are the density operators projected into these bands, and you get again these form factors which come out of the projection. And these are the reason, the only reason for the non-triviality of the Hamiltonian. Okay? And the other difference is that unlike before, I have a dynamic negative 2 Hamiltonian, which is a positive Hamiltonian. So instead of the charge to respect to the gapless, I would expect some mutual separation to the gapless. Okay? This is still a positive semi-definite Hamiltonian, as you can see here. And as pointed out in these papers, first by Hamilton by others. I think they are also spoken about the people are also spoken about this. Okay, and since they spoke about this, I'm going to go a little bit faster. The same methodology applies. Since the forest is semi-definite Hamiltonian, you can find an eigenstate or a ground state if it annihilates, if this operator annihilates it. Okay, because it's diagonal O, if this annihilates it, you found the ground state. And these ground states turn out to be ferromagnetic states, where you just fill these bands, these flat bands, in some bases, in the third basis here. You just fill them, there's 8 flat bands, and you just fill them in a preferred way. To understand which preferred way, to understand it really nicely, I would need to go to the heavy Fermion, because I can't find to go to that. There's some way to fill them in. It involves value coherence. If you don't assume translation symmetry break, it involves some value coherence, etc. The best way to understand that is by mapping the whole forms. Okay, now what I did want to get to is the charge spectrum. So now you can see very nicely that the same method of doing the charge spectrum that we did in the uniform pairing also works here. So I activate the C dagger on my ground state. It just gives me a rotation in the same spectrum. It doesn't couple to electrons. So I can just diagonalize this matrix. And this matrix is kind of like, this is for the charge 1 acceleration. And this matrix is just the Coulomb potential, which now has a Q dependence. Okay, it's squared times some form factors. Okay, in the previous case, in the case of Jordan and White, this was coming down to dependence, and this was, just this became identity by the uniform pairing condition. But if you don't have uniform pairing condition, okay, which the crystal binary graphing does not, then the charge spectrum itself, charge 1 spectrum, gets a dispersion. So remember, in the uniform pairing condition, the charge spectrum is flat, the charge 1 spectrum is flat. But in here, the charge 1 spectrum gets itself a bandwidth, and this bandwidth is basically the Coulomb, is basically the Hubbard U in my heavy thermal description, and we can see the bandwidth of the charge spectrum. Now, again, some things such as the curvature here or the flatness here can be explained, but not in the strong optics picture, momentum picture, but then some other pictures. But the moral of the story is that the one thing that changed from uniform pairing to non-uniform pairing, everything else is basically the same, is the charge 1 spectrum got a dispersion. Even though your flat band didn't, your initial flat band didn't have any dispersion. This, okay, it has some small dispersion, but this is huge. This is of order U, of order T dispersion, the Coulomb interaction. Whereas, even if I made the crystal binary bands exactly flat by changing some parameters, I would still have this dispersion as large as this. So that's what non-uniform pairing brings. It brings the dispersion of the single particle excitation. Dispersion of the single particle excitation brings you particle-particle continuum or particle-hole continuum. In this case, this is the exciton spectrum or the neutral spectrum, which again can be solved exactly for these problems because you can act with the neutral state with a neutral operator on the ground state, and it turns out that for these problems which psi is an exact state of ground state in this Hamiltonian, you can solve this exactly. It just involves a matrix which you can diagonalize. Okay, it doesn't couple to partons, etc. in this case. Okay. So it's a very nice spectrum, and what you get in this case is you get this particle-hole continuum, and you see because the particle of the dispersion, the particle-particle continuum is going to be very dense. Yeah? But then you see the Goldstone modes now, and this is how you know that these states are ferromagnets. So you see some Goldstone. So this is a Goldstone mode in the neutral sector, and you can see clearly the Goldstone stiffness. Okay, it's also related to the quantum properties of these bands, etc., etc. So here it becomes much less clear. Coming back to another question, it becomes much less clear that I'll be able to tell you that if you show me the spectral picture in a flat band, because the non-uniform pairing, the uniform pairing condition is not satisfied. The charge 1 acceleration has a dispersion, and then all the other accelerations have dispersions, although we can clearly see that the Goldstone spectrum, the bound state spectrum, is actually has some structure. For example, there's a Goldstone zero energy, and then it has some flat bands, which are actually heavy thermal bound states. Okay, and because here we have a Hubbard U model, okay? Impulsive Hubbard U model. This is the charge 2 spectrum. So unlike our negative Hubbard U model, here you see no bound states in the charge 2 spectrum. Okay, which, and I'll end with this. So you see anti-bound states in the charge 2 spectrum, and these anti-bound states are quite flat. Okay, which means they're actually bound states of putting two heavy fermions together. Okay, on the same site. but you see no bound states. And this is a generic feature of positive Hubbard-U Hamiltonians. Positive Hubbard-U Hamiltonians, projected Hamiltonians, cannot have Cooper pairing. So there's a theorem, well, we can prove a theorem that basically tells you that these things which are called conmuttant pairs basically could give you pairing out of repulsive interactions through, fluctuations. So you put a vertex of an RPA in the interaction, and you get the fluctuations, you get attractive channels, some higher harmonic. That cannot happen for projecting other Hamiltonians. So it's for zero kinetic energy. So you need kinetic energy reduced. So these projected models where I have zero energy cannot be complete for crystal binary. I need to add either kinetic energy to them or some postulate some attractive interaction, etc. So with that, I'll stop and take questions. Thank you.
Okay.
Yes, I have a question going back to this uniform pairing condition. In terms of the momentum space, how should I think of it? Is it just means that simple space, intra-orbital simple space, right?
So the uniform pairing doesn't care about the offsite. Okay, so this is the condition. The condition comes out of the fact, okay, that you want to, when we expand this Hamiltonian, you get these square terms, okay? And what you want to be able to do is, if these projectors, the diagonal parts is the same, right? You can just add these projected operators and you get the projected number of it. So the quantum number of this total one, it's just the number of states in your flat bands, just the number of particles. Right? So this is the quantum number. So what you want is this diagonal part, right? So you see, it doesn't tell you a condition on B alpha beta with beta molecular delta. It just tells you a condition on the diagonal part, okay? And this can be implemented if you have some symmetry. Okay, so if you have some symmetry of your model, irrespective of how your model looks, okay, if I have some symmetry that relates A to B, okay, then P projected in some band of AA will be equal to P of BB. Okay, if I have a symmetry in one orbital per site, right, because the symmetry just changes this to this, and basically this means that the occupied number of states on the other side is, can be added to the down the present if you decide to get the forward. So it doesn't say anything about the PA.
It doesn't say anything about the specific form of the pairing, whether I can have P-wave pairing, D-wave pairing.
This is all S-wave pairing.
It's all S-wave pairing. I mean,
in order, if you want D-wave or other types of pairing, you got to modify your Hamiltonian. Okay. And this is all S-wave pairing. You can see it's here. Okay. S-wave singlet. If I want D-wave, etc., I will need to modify my Hamiltonian. You can get that. These are models, right? To build a model, and then these are like the same. So look at these exact models. That you can. So I cannot get. It's not related to the type of pairing that you have. It's the pairing. The symmetry of the pairing is just given by your Hamiltonian. So if I wanted, if I wanted a D-wave pairing, which would be whatever C. I would have a nearest neighbor, okay? Then I would need to write this beta operator, and if I want an exact pair, I need to find a Hamiltonian with which it commutes. But this is all for S-wave pairing.
Can I ask
one question? In these models.
One more question. Going back, relating to your talk yesterday, you showed that in real materials, mostly these flat bands doesn't come with a nice gap, right?
Right.
So now this projection process, you said that you need to have U versus the gap to be, that's important, right? So I'm saying that except the case of the TBG, which seems to be have a little bit of the gap between the flat bands with the rest of the bands. So it seems that we're gonna have a problem, right, of this projection process.
Well, you're going to have a problem. You always have a problem if you try to apply a theory based on the wrong, manifestly wrong assumption, right? So you apply a theory that's based on projecting to a flat band that's separated from other bands to a flat band that's just point, you might have problems. It's not entirely clear that you will have problems. For example, look at twisted triangle. Okay? Twisted triangle, we have these bands, and even these, this is the McDonald bands here. They're not very far. Yeah. Right? They're not very far. They're within Coulomb. But then in twisted triangle, we have this Dirac node is here.
Yes.
You have a gapless system, okay? But the Dirac node has such high velocity that at least at zero displacement doesn't do very much, right? So it depends on what type of crossings we have. So for example, here I would say that likely this crossing won't do very much. Probably this one might, because it's a quadratic, etc. So these things need to be sorted out. But we're still in the infancy of all these theories, especially when formally applying this to actual materials. And this needs some exciting time for all of you, young people.
Thank you.
Thank you.
Okay, question?
My question is, did you choose some symmetry breaking basis for your interacting model? Because you got a mode, and so there must be some spontaneous symmetry breaking.
Sorry, I couldn't hear you. I couldn't hear the question.
Oh, sorry. My question is, is it better? Okay. My question is, did you choose some symmetry breaking basis for your interacting model? Because there's some spontaneous symmetry breaking. You get some Gaussian mode, so you must somehow break your symmetry somewhere.
That's right. But these states here are ferromagnets. Ferromagnets in some large symmetry group. Actually, depending on the parameters, are the ferromagnets U4 or U4 times U4, right? And these are these Gaussian modes. So if they're correct, these states do break, spontaneously break the symmetries. They have the ferromagnets, some large symmetry, which we can, which probably are on the level of these U4 times U4. I think, I'm not sure, but so right. So these states, these states are ferromagnets that break those symmetries, and as a result, as you said, you get Gaussian.
Okay, thank you.
Thank you. Very good question.
Okay. There are no more questions. So let's thank our speaker again. Thank you so much.